So just a very quick reminder, all the physicists know this, some of the mathematicians who maybe haven't seen this picture before. So we have a correspondence between the dynamics of a conformal field theory. You can think of it as open strings on a stack of branes, and closed strings propagating in one higher dimension in anti-de Sitter space. And there's one physical model here. And this one physical model has a coupling constant, G squared, which in terms of the Yang-Mills coupling constant is this famous Tooth coupling, G Yang-Mills squared times N. So there's one physical model, but the physics words that you use to describe the model conveniently are very different when this coupling is small versus when it's big. When the coupling is small, the physics is well described in a simple way, close to weak coupling, in terms of gluons. And here, the expansion for any interesting physical quantity like scattering amplitudes is in powers of G squared. But when the coupling constant becomes huge, of course, this expansion becomes crappy. And the incredible thing is that there's a new expansion in a different parameter. The parameter is 1 over G, not 1 over G squared, but 1 over G. So 1 over the square root of G squared. And you can interpret this expansion as for the same physical quantity as calculating something involving string theory in living in one higher dimension. Okay, so that's the famous holographic duality. And of course, by now, this is, I mean, it has not been proven, but there's 10,000 checks on it in 30,000 papers. And maybe one of the most famous quantities that, again, all the physicists will know, where this has been, where some of this magic is understood in great detail, is the famous cusp anomalous dimension. So one way of talking about this is in terms of amplitude is if we take the 4-particle amplitude, we know that the 4-particle amplitude is actually really strictly 0 in this theory, because you emit arbitrarily many gluons from soft and collinear emission of gluons. But this amplitude is a tree amplitude. And if I put some cutoff on soft and collinear emission, then I get something exponentially small. Not 0, but exponentially small. It goes like exponential of minus 1 over epsilon squared, where this is really a stand-in for the product of a soft and collinear logarithm, times a function of this coupling constant G, gamma cusp of G. Okay, so this is a probe. This is an observable of the theory, and it's a probe of the theory. And the gamma cusp of G has been famously computed using all the powerful machinery of integrability for n equals 4 super Yang-Mills already in the mid-2000s. So I would just want to show you what the answer looks like. And here I'm borrowing a very nice organization, which I'll be using a little bit more of in a second, of a paper that Lance told me about that he wrote with Benjamin Basso and Georgios. So the solution to the cusp anomalous dimension is given famously by this BES kernel. So one defines a certain matrix, a certain Kij, a matrix Kij, by this formula. These are Bessel functions here. So you see it has a dependence on the coupling constant G there. And then starting from this matrix, they like to organize it in this way. You build it an infinity by infinity matrix where there's an odd block, an odd even block, and an even block. This is where I and J are odd and odd, odd even odd, and even. You take this infinity by infinity matrix, you add 1 and you invert it. And you look at the upper left corner, the 1, 1 component of this matrix, and multiply by 4G squared, and that gives you the cusp anomalous dimension as a function of G. Okay? And at this moment, you know as much as I do about how this actually works. Okay, so this is, again, all the magic of integrability, et cetera, goes into this incredible formula. Very simple, but still rather mysterious formula for where this comes from. But from this formula, you can learn a number of things about what gamma looks like as a function of G. So here I'm just plotting gamma cusp divided by G. So it starts linear at low energies and it flattens out, linear, not low energies, at small g, and it flattens out at large G. And if I write in terms of gamma itself begins as 4G squared, then it has a two-loop correction that looks like minus 8 zeta of 2G to the 4th plus ... So this is the sense in which we have an expansion in powers of g squared at low energies. This is the gluon expansion, the perturbative expansion. But at strong coupling, it asymptotes to 2g, and then there are corrections that are powers of 1 over g. And you interpret the corrections of powers of 1 over g as coming from string loop effects in empty de Sitter space. Okay, so that's what's kind of remarkable. It's not like as you go to strong coupling, big G, totally insane things happen, everything goes totally haywire. You go from one tame expansion at weak coupling, when G is small, to another tame expansion at strong coupling. And I think I'm not very far from an expert in this business, but one of the funny things about it from far away is that people do this incredible hard work. They do all these tour de force calculations, get all these results, and all the curves always look like this. Okay, all this hard work just goes into almost featureless curves that always look like this. And that's kind of the magic, is that this system has two limits where it's simple, but it's simple in totally different variables. Okay, so in any case, the very beginning of understanding the emergence of empty de Sitter space is just to see why this happens. How does it happen that if you take this expansion of small g squared and somehow extrapolate the big G squared, that you get something simple on the other end? All right, we can also ask of the analytic properties of this gamma in the complex G plane. And in fact, this gamma of G has a branch cut that starts on the imaginary axis at a value of G star equals 1/4. Maybe I should put I quarter here, okay? And down here around the origin, this power series expansion actually has a finite radius of convergence, and the radius of convergence is just given by where the branch cut starts, as you'd expect, okay? The other expansion at this end is actually asymptotic. So this does not, this is an asymptotic expansion on this end, but the expansion around the origin actually has a finite radius of convergence. Okay, so this is what's known about the cusp-anomalous dimension, at least qualitatively. And in this very nice paper of Lance and Benjamin and Georgios, they showed how exactly the same matrix, twisted a little bit, also contains many other kinds of gamma cusp, which show up in other places. Okay, so you take this matrix and now you put a cosine and a sine and a sine and a cosine there. You define gamma in the same way as before. You just take 1 plus k inverse 1, 1, multiply by 4g squared. So if you put alpha equals 4 pi, that goes to the old cusp anomalous dimension. But for example, they consider two other values. I'm just going to talk about one of them. The other one we don't have some interpretation for yet. But anyway, there's this one at alpha equals 0 that they call gamma octagon of G. And this is also an object that shows up in scattering amplitudes. It doesn't show up in the 4-point. It's not the cusp anomalous dimension, but it shows up in the 6-point remainder function. As U1 and U2 and U3 goes to 0, there's a log squared divergence there, and the coefficient is gamma octagon of G. Okay, so and this gamma octagon actually has a very simple explicit expression, and this is why I want to write it down, because it shows you an example of a function that does some of the correct qualitative things. Okay, so gamma octagon of G is this funny, nice formula, 2 over pi squared log cosh 2 pi G. And you see, this almost has all the properties we want for the answer. At small g, it goes like G squared, and it's clearly a series expansion in G squared. But at large G, cosh becomes exponential and just goes like G. Okay, so that's kind of cool. If you want to see something that starts as G squared and asymptotes to G, it's hard to write down a simpler expression than log cosh G. However, this does not have all the qualitative properties of the cusp anomalous dimension. First of all, at large G, the corrections to this are exponentially small in G. So that means that all of those string loop corrections, which are powers of 1 over G, are missing in this formula. And another feature is that the analytic behavior of this in the G plane is not quite the same. This has poles. Okay? This is a very simple expression. It just has poles. Has the same radius of convergence at 1/4, but instead of a branch cut here, it has poles. Okay, so just keep these two kind of functions in mind. The cusp anomalous dimension, there isn't a closed form formula for it, but it comes from inverting this matrix. It has this branch cut structure, and it has a series expansion in G squared at small g squared and G, and then powers of 1 over G at large G squared. And then there's this very simple object, large cosh G, that has similar asymptotics, but is missing some of the physical feature is missing these string loop corrections and has this funny different analytic structure. Okay. Now, I mean, of course, a natural question is, can we get non-perturbative results like this without the heavy machinery of integrability? Of course, heavy machinery is spectacular, and it's given us all the data, the most spectacular data we have about this theory. But we certainly believe that this sort of transition from gluons in a CFT to strings in anti-de Sitter space is a very general, robust phenomenon. And it should not rely so heavily on integrability. So it would be nice to have some way of thinking about this, at least some picture for what is going on that does not rely so heavily on having integrability. And, you know, of course, an old fantasy that people have talked about is, why don't we just sum all the Feynman diagrams? Okay, if we could somehow directly sum all the Feynman diagrams and then just then we'd have to figure out, to perturbative expansion, how do we then take it to a strong coupling? But the hope is that there is some way of recognizing the sum as a solution to some equation where g squared just appears as a parameter in the equation rather than an expansion parameter. And then you just take g squared to be large and you solve the same equation to get the results at strong coupling. And people have actually done this, not obviously for summing all Feynman diagrams, but for summing classes of Feynman diagrams. A famous example is when you sum these so-called ladder diagrams. Okay, and this is now in the case where all of these legs are massive. Otherwise, these would all be divergent. But if all these legs on the outside are massive, you can take the box, the double box, the triple box, and this whole ladder. And this entire sequence you can actually sum exactly. The reason you can sum it exactly is kind of cool. It's because, in fact, even before summing everything, you can actually get the answer for this box without doing any integrals. And that's because if I think of this as a function of the external data, x1, x2, x3, x4, and also as a loop integration point, x0, then it's clear that if I hit with a box on this external point x1, I'm going to collapse the internal propagator, and then I'm just going to get 1 on the right-hand side. Okay? Or in general, by the same logic, if I hit with the box on x1 with i+1 ladders, I'll get the function with I ladders. So therefore, if I do a generating function for all of these guys, and I write it like that, then there's a formula that box f plus g squared f equals 0. And now that comes the last point, that all of these integrals depend on just 2 cross ratios z and z bar, which are a function of the x's. So you can easily convert this box into some differential operator involving the z's, okay? And so this structure that goes into summing the ladders shows up as a certain differential equation that's satisfied by this generating function. And now this has exactly the form that we want. If you take this generating function and you think of g squared as small, it has a solution as the sum over these ladders, but then you can solve exactly the same equation when g squared is huge, and that just tells you what it looks like. Or another way of saying it, you can just solve this exactly once and for all and just see what happens as you take it to large g squared. Even better if you could do that. But if you couldn't do that, you could even just take this equation and just make g squared huge and do an expansion in powers of 1 over g squared to see what happens. All right, so people have done that, and they've played with various very interesting perturbations on this idea. But it's clear that this is not going to give us the like stringy behavior. And already, if we're talking about the 4-point function, it's qualitatively clear. We've known since the 1970s that somehow it's when these graphs become dense and not sort of long and skinny, but they become sort of large in 2 directions, that some kind of stringy picture is going to emerge. And this is a deliberately vague statement that we need to see the dependence on some other direction too. Okay, not just a sort of direction of getting longer and longer, but some other direction. But then it's hard to see what that other direction could be. I mean, you only have these few kinematic variables. If you're looking for some kind of differential equation or something, where's the other variable somehow? You know that you need to have access to, like, you know, more stuff, see this other direction, but there doesn't seem to be any other direction to exploit, at least as far as the sort of kinematic dependence goes. Okay. All right. So but that's the strategy that we want to talk about now. But so that was just all motivation. Now let's go back and ask a different question. In n equals 4 super Yang-Mills, there's this, there's this interesting fact that we have these extremely simple objects like the cusp anomalous dimension that are associated with a divergent quantity, the infrared divergent part of the log of the 4-point amplitude. That's an extremely simple quantity, depends on one variable, gamma of g. And so anytime, we have a function of very few number of variables, you can go to town on it and hope to solve. But then, especially when we talk about amplitudes, there's a jump from there to when we talk about finite objects like the remainder function, which are already more complicated. They begin at 6 points, they depend on 3 variables, and more, but they're more complicated objects. A 3-dimensional space of variables, they're more complicated object. It would be nice if there was a simpler finite object that we could talk about in n equals 4 super Yang-Mills. And there's a beautiful such finite object that, people have talked about this. I first learned about it in a paper of Johannes and Fernando Aldai, but I think other people have talked about it before even. And what it is just the ratio of a Wilson loop with 4 points and just adding an insertion of a Lagrangian as a 5th point. And if I take the ratio of this guy to the 4-point Wilson loop, as usual, the infrared divergences cancel out. And I'm left with a function now of the only cross ratios that I can make with this 1 point in the 4 points, which is actually a single kinematic variable. Okay, so this is a function of the Tupf coupling, what I was calling g squared before, and just a single variable z. All right, so this is the sort of physical definition of what this guy is, but it also has a very nice definition, sort of purely in terms of amplitude data. We know that if we take the logarithm of the 4-point amplitude, that it's only log squared divergent. So at L loops, the logarithm is some L-fold integrand, and the fact that it's only log squared divergent means that if I integrate 1 loop, 2 loop, 3 loop, 4 loop, if I integrate everything out but the last loop, if I integrate out L-1 of the loops out, I get something finite. It's only that very last loop integral that gives me a log squared divergence. So the way to interpret this is what you get by integrating all but one of the points of the loop integration points out. And so you look at the dependence on this final loop variable. Okay, so that's a very simple finite observable. And now what we're going to talk about is how this finite observable is actually naturally computed by the amplituhedron. Okay, so we're going to interpret this observable in the language of the amplituhedron. Apart from anything else and going to strong coupling and all that stuff, this, I think, mathematically and physically is an interesting thing. We've been talking for years to many of our math friends about amplitudes and positive geometries, and the fact that when you integrate, you get polylogarithms. And certainly, I can tell you, whenever I talk to Sasha Goncharov about these things, you'd always say, "Oh, please show me a space. Let's do it. Let's try to integrate." And then why don't we just take the forms and integrate them and see how we get polylogs? And I'd have to say, "Oh, well, sorry, Sasha, they're actually a little bit divergent, and you have to subtract this and do that." And so then it immediately becomes a little more complicated, less clean. We're now going to talk about something where there's a positive geometry, directly a positive geometry. You do nothing to it but integrate the form, and you get a finite set of polylogarithms out of it. Okay, so that's what. So minimally, that's a setup where there's no excuses anymore, right? You have a positive geometry, you have some polylogarithmic thing, and we should be able to understand how the two of them work. Okay, so. So let's talk about, and in fact, what we're going to see is that even the whole idea of taking the log of the amplitude and not integrating everything but one out, all of this, which from the conventional perspective is very physical. We know these things work. We know we take the log of the amplitude because the IR divergence exponentiates. There's a lot of physics words and intuition that goes beyond that. We'll see that all of that is a totally trivial consequence of the combinatorics of the amplituhedron. It's trivially natural from the combinatorics of the amplituhedron. But what I'm now going to have to do is talk about the loop amplituhedron. And I think even the sort of some of the mathematical investigations that have been done on the amplituhedron have mostly focused on the tree amplituhedron, which is already, of course, it's a very interesting object. But as I keep telling my mathematician friends, the loop amplituhedron is like 1 or 2 orders of magnitude more interesting than the tree level amplituhedron. Involves many more physical and mathematical novelties. So I think there's anyway that there's a lot going on with the loop level amplituhedron. But here I'm just going to talk about the most simple case of what this looks like, which, however, also has the most amount of the novelty associated with the loop amplituhedron in them, which is the 4-point L loop amplituhedron. So let me just define what this is. In the usual picture where we think about every loop as a line in P3, so A1, B1, A2, B2, and so on, where each one of these are their individual G24s, and I have the external momentum twistor data Z1 through Z4, because I only have 4 particles, I can just put these to some identity block, right? 1, 0, 0, 0, 1, 0, and so on. So these Zs are just locked to the identity. Then what does it mean for this configuration of L lines to be in the L loop amplituhedron? Well, first, it means that each one of them by itself is in the 1 loop amplituhedron, which in this case is nothing other than saying that the minors A, B, 1, 2, 1, 3, all the minors of each one of these thought of as G24s are positive. Okay? And here it's especially simple because we're just at 4 external points. So there is the cyclic ordering on the external points. So I am talking about these minors being positive, but it doesn't relate them to each other at all. Each guy individually needs to be inside the 4-point 1 loop amplituhedron. All the magic and all the novelty of the loop amplituhedron has to do with the second statement of mutual positivity. That each one of these ABs, if I take one 2x4 matrix associated A1, B1 and with A2, B2, each one of them individually has positive minors, but if I stack any pair of them together, all the 4x4 determinants have to be positive. The reason this is novel is that unlike the usual notion of positivity that we talk about with the positive Rachmaninian, the amplituhedron, and so on, where some kind of cyclic ordering is crucial, in the loop amplituhedron, this statement is complete permutation invariant. There is no ordering on this side. Okay? It's just that any pair of ABs are a positive. Okay, and so if I wanted to represent what this positive geometry is, one way I could do it is to draw a graph with the vertex for every AB. So there are L vertices here. I connect any 2 ABs which have an inequality AB alpha, AB beta positive, so I just get a complete graph here. Okay, so I have a complete graph. Every line in this picture says that ABI, ABJ is a positive. So this defines the positive geometry together with this independent condition on each AB separately. But we're going to forget about this from now on. It's all about this condition. All right, so that's the L loop 4-point amplituhedron. The canonical form for this region is supposed to give us the integrand for the L loop 4-point amplitude. All right. So now what we're going to do in the rest of this talk is 2 things. So one is just purely, really trivial combinatorial. Even calling it combinatorial is overkill. We're going to see why from the amplituhedron it's actually very natural to discover that the log of the amplitude is an interesting object, and that the log is actually given as a sum over what you can call negative geometries. And what I mean by this is that we'll discover that first, the log is interesting, and secondly, that the log is expressed as a sum over these quote unquote positive geometries, where I draw the same graphs. These graphs are connected. They're connected graphs, but now every one of these lines means that the corresponding ABs are negative, and instead of being positive as they were for the amplitude. This is interesting because in this picture, you can very easily see that every single one of these terms gives you, if you leave one point unintegrated, so first if you integrate over all the points, every region by itself is only log squared divergent, just like the full log of the amplitude is, but each region here by itself is only log squared divergent. And therefore, if you leave one of the legs unintegrated, every one of these regions by itself is going to define a completely finite function of Z. and that's what I was advertising. These negative geometries are associated with polylobes. And so that suggests a kind of a deformation of the amplitude with a new parameter. Okay, where, and as we'll see, when you start working out these positive geometries, you see that it's easy when these pictures are trees, and it gets harder when, you know, it's a snake eating its own tail. When you say this is negative relative to that, which is negative relative to that, which has to be negative relative to that. When you have loops, it gets harder than when you have trees. And when you have more loops, it gets harder than when you have, more loops is harder than fewer loops. So we're going to introduce a parameter that's kind of natural from the perspective of organizing or thinking about the positive geometry. We don't know what this parameter means physically. Let me call it y to the L, but it's going to count the number of loops in this diagram. Now, it stresses has nothing to do with the loops of the number of loops of the problem. It has nothing to do with the number of loops, which are the number of green dots here. That's the capital L. This is the number of loops in this funny connected graph. Okay. So this is a deformation of the amplitude of this parameter y, and we're going to solve for this deformed amplitude in the limit where y is 0. In other words, we're going to learn how to sum all of the tree graphs in this picture. So it's not the amplitude, it's some deformation of the amplitude, but we are going to be able to solve it non-perturbatively in the 't Hooft coupling. Okay, and what we're going to find is that the resulting objects we get, and then from that object, we can extract something that looks like a quote unquote cusp anomalous dimension. And remarkably, that cusp anomalous dimension has all the same qualitative properties as the exact answer. It looks like G squared at low energies. It asymptotes to G at high energies. It has a series expansion in G squared, sorry, at low G. It has corrections like 1 over G at high G. It has a branch cut. And anyway, I'll tell you more about the more detailed comparisons between the two of them. But that's what's interesting, that this essentially totally trivial combinatorial fact, together with an, importantly, I didn't tell you how we did the loop integrals, but despite the fact that these pieces do not have interpretations as Feynman diagrams at all. We don't know how to interpret these pieces as Feynman diagrams. Nonetheless, it turns out that exactly the same boxing trick that worked for those latter diagrams works here. And so we instantly write down a differential equation that these things satisfy. But it's a more interesting differential equation. So it's a nonlinear differential equation. And that nonlinear differential equation is what's responsible for getting all of the qualitative match between small g and large g. So I would say that, that most of the magic here is just in this sort of trivial combinatorics. And then there's just a little bit about how the boxing allows us to avoid doing any integrals. But I think the most interesting part is in the reorganization of the answer in these terms. Okay. So so let's begin. So let's first talk about why you would ever think from the perspective of the amplituhedron that it's a good idea to take the log of the amplitude. You've never heard of infrared divergences and none of that stuff. Well, there's a very natural thing to do. This looks complicated, right? Where we have all of these things are mutually positive, but it's clear at the level of the positive geometry that if we say that these two ABs are mutually positive and we add the region where they're mutually negative, well, that's like putting no restriction between the two of them at all. So there is a sort of obvious formula that these guys being positive is no restriction minus these guys being negative. And therefore, this geometric region is expressed as now a sum over all graphs where all of these curly lines are replaced by straight lines, which means that they're mutually negative. And in general, this will disconnect the graph. So there'll be many disconnected components of this graph, okay? But once you see this, once you see you have the sum of something with many disconnected components of a graph, you know what you're supposed to do. Whenever you get the sum of a bunch of graphs that are disconnected, you take the log, okay? And the log is now the sum over all the connected graphs of exactly the same type. So just combinatorially, once you realize that you write plus as nothing minus minus, then it's very natural to look at the logarithm of the amplitude and get the sum over these negative regions. And now here's the cool thing. It's guaranteed that every one of these regions by themselves, despite the fact there's no Feynman diagram interpretation, if you take the canonical form associated with them and you integrate over all of these loops, you'll only get something log squared divergent. Okay? And there's a very simple argument for that. Oh, sorry. Let me say one more thing. What we should do then is we want to fix one of the loops and not integrate over it. And so just taking the sum of these diagrams, and I'm just always going to denote the loop that I'm not integrating over, the last loop with this x. Then there's a sort of trivial, obvious graphical expansion now where everything gets rooted to this x. So I have this x, can connect to one guy, two guys, and so on. There are symmetry factors. Sure, there should have been a 1/2 factorial in front of this term and in front of this term as well. But anyway, it's just some overall graphs with symmetry factors appropriately. And as I said, every one of these, now I'm not integrating over this last point. So every one of these geometries, when I do integrate over the rest of the loop momenta, is going to give me a function, a finite function. And of course, we expect them all to be polylogarithmic in this case. And they're indeed all finite. And up to 4 loops, Yara and Johannes, I think, have almost all the regions calculated. Sorry, up to 3 loops when we have 3 of these things that we're integrating over. But anyway, here's an example. This very simple one is pi squared plus log squared z. This guy here is some weight 4 function, some weight 4 harmonic polylog with some corrections that we can, anyway, so all the expressions and these simple low point cases are known, but I'm just sort of stressing here, every one of these is some finite, interesting object by itself. And there's a very simple reason why we get something finite here. We know that all of the infrared divergences come when the lines AB are in the collinear regime, which in the Twister language means when AB passes through 1 while lying in the plane 4, 1, 2. And what you can see here is that if you go to that configuration, then demanding consistency, demanding that all of these guys are in the one loop amplituhedron forces all these minors to be positive. So for instance, this configuration says that I can write A is 1 and B is 4 plus x2. And you can see that demanding that AB alpha be inside the just the ordinary positive G24 here, the one loop amplituhedron, forces x to be positive, and yet demanding that all of these ABs are mutually negative forces x to be negative. So there's no residue in the soft collinear regime. And that's why there's no divergences here. Okay? There's no residue in the soft collinear regime, so that's why we get something finite. And that's why it was crucial to flip this sign. Crucial to flip the sign to get something, to get something finite. All right, so now we don't know how to sum all of these. We don't know what the canonical forms are for all these regions, but we do know what the canonical forms look like for all the regions that look like trees. And I hope that's clear why we know that, because when it looks like trees, there's always just one guy that you can solve for the inequalities demanding that the ABs are negative relative to each other by pruning the tree, going from the outside in and pruning the tree recursively. Okay, so that lets you determine the positive geometry trivially, and it also lets you determine the canonical form trivially. And you really begin with the canonical form that you see already at 2 loops, which has some interesting numerator, and you just literally multiply by those numerators as you go along. Okay, so that's why by pruning the tree, we can get the canonical form for those regions. So because we can get the canonical form for those regions, let's see if we can sort of sum those regions and see what happens. So we want to ignore all the other regions and only look at the generating function that we would get here if we summed over all the trees. Again, here's another extremely simple bit of combinatorics. If I say that I'm going to define a generating function for all the trees, which is the one that starts with this x, but then has any tree here. Let me also define this other thing that I'll call H tree, which is where you come out of this root to a black dot, and then you go to trees here. So in other words, this does not include something where points, the lines come out of, many lines come out of this x at once. Okay, those are trees that are not included in this H tree. Here I have to go to one guy, which from here can do anything at once. Okay, well then it's clear that that the full generating function for all trees is just the exponential of the one where you first go out somewhere and then branch all you want. Okay, so this is another interesting exponential relationship between the, it's different than the usual disconnected one. Anyway, it's another very simple exponential relationship between generated functions. Okay, now all of this is important because we can actually easily, we can not only determine the canonical forms for all these regions, including the H trees, but because the H trees have this extraordinarily simple dependence on this last point, because it only knows about one more that it connects to, there's a boxing formula for all of these canonical forms. If I take the box with respect to x naught of anything, wherever it goes, I just collapse the x naught onto wherever it connects to. So box of x naught on this thing will just give me x1. Box of x naught on this would again just collapse x naught onto whoever it talks to. And so in general, box x naught on a picture that looks like this, where here any tree comes out, is just g squared given by collapsing this guy on that guy. Notice this important minus sign here. I should have maybe stressed this. I should have stressed this early on. You will notice that all these expressions, I didn't write them out enough, but obviously the fact that we have a finite radius of convergence here means that the series expansion is alternating in sign. Okay, so the actual signs you get are alternating. That's very important for it having a finite radius of convergence. And yet, of course, when we talk about the integrand, is g squared plus g to the fourth plus g to the sixth, all plus signs. Okay, but we actually got these minus signs in an interesting place. We got the minus signs from exactly this move. When we wrote that this plus is no connection minus the negative region, now we get all these -1 to the number of edges. And then when we root that through, when we follow that through for the trees, there's just a minus sign, -1 to the number of edges of the graph. And that minus sign, so first, that gives a natural alternation. And secondly, in this formula for the boxing, there's a minus sign here, okay? Because of that underlying minus sign. Okay, but now, remember I told you before in the case of the ladders that the box of x naught was a very simple differential operator in terms of those two cross ratios, z and z bar for that problem, where our problem just has one variable, z, so it's an even simpler differential operator. The box operator is just z d by dz squared. Okay, and so this equation, boxing equation, tells us that z d dz squared of the h tree plus, now this is just a sum over all trees. But we just learned a second ago that it's related to h by this exponential formula. Okay, so from here we get this interesting differential equation that z d dz squared h tree plus g squared e to the h tree is equal to 0. So this is a beautiful, famous differential equation. It's just the Liouville differential equation restricted on the real line. Liouville is a function of two variables, but it's Liouville on the real line where z equals z bar. I don't have time to explain it, but we actually have a boundary condition that we know. Remember, I told you that the integrand for the canonical form is just multiplying by all these two loop numerators, and we know that all the numerators vanish when z equals -1. So we know there's a boundary condition that where h vanishes when z equals -1. And so that's going to allow us to solve it exactly in, well, so we can give the, it's an exactly solvable differential equation. We'll give the solution in a moment. But I want to stress one aspect here, which is very different than the latter case. Remember the latter case, we had this sum just in one direction, and that's reflected in the linearity of this differential equation. Here we have something nonlinear in the differential equation. That nonlinearity is coming from the fact that the trees could branch. Okay, and so when I said this vague thing in the beginning, we want to see another direction. Here we're seeing this other direction emerge, not in the kinematical space of the problem, which only has z, but somehow in the space of all these different amplituhedral negative geometric regions. That's where the kind of branching is taking place. That's where the extra direction is. And that's what changes the structure of this differential equation from this simple linear one to this nonlinear one. I'll come back to the analog of these ladders for our problem in a moment. Okay. All right. So Now let's solve the differential equation. Okay, so it has this very simple solution. If I go back to the full tree, just the exponential of this, and it's just given by this extremely simple formula. It goes like z to the a over z to the a plus 1 squared, where a is determined by this by the boundary condition that I told you is determined by this formula. Okay, so this capital A, when g is small, scales like 2g, but you can track what it does when g becomes very large and it approaches 1. So when I expand this around, this thing approaches something rational, it just approaches z over z plus 1 squared as the coupling becomes huge. And you can expand it. It has a series expansion in powers of g squared here and 1 over g and not 1 over g squared at the other end. Okay. So given this expression, we can actually extract gamma cusp from it. Okay, so what we have to do is now integrate over this guy was finite. We have to integrate over the last point and extract the logarithmic divergence from it. Okay, and Johannes and Fernando had a very simple prescription for doing this, which is that you just expand this guy out, and everywhere in the integral you have some power x naught to the p. This gets replaced by sine pi p over p. And it turns out that on this explicit expansion here, this very simple prescription allows us to actually do it exactly. I'm skipping the details for how it works, but it's a 3-line computation. This integral is actually related to not the gamma cusp directly, but the g ddg of the gamma cusp. And so we get this nice formula. The g ddg of the gamma that we get from summing over all the trees is given by this simple expression, 4 over pi a tan pi over 2, where a again is determined by that formula that I told you before. And so we can work out what our gamma cusp looks like. Okay, so our gamma cusp tree at small g looks like 4g squared minus 8 zeta 2g to the 4th plus dot dot dot. Again, just a perturbative expansion. At large g, it looks like 4 over pi g, some correction of order 1 over g, and is a series expansion in 1 over g. And it's kind of cool to see why we went from g squared to g. It has to do with solving this formula. You see, if I take this formula and I imagine I'm solving it for a, if I'm solving it around g goes to 0, because a is going to 0 as g goes to 0, the solutions for a will be even in g. Okay, because cosine is even. So because I'm expanding around a symmetric point for this function, I get powers, an expansion in powers of g squared. But when I go to large g, I'm expanding around a equals 1 and g goes to infinity, and that breaks the symmetry between g and minus g. I'm not expanding around minus infinity, I'm expanding around plus infinity, and that's why I get an expansion in powers of 1 over g and not 1 over g squared. Okay, so there's a simple reason why we get expansion in powers of 1 over g and not 1 over g squared at strong coupling. Okay, so again, this is exactly the qualitative behavior of the cusp and almost dimension. This number, of course, matches basically by construction gamma cusp at small g. The behavior at large g, the coefficient is different than the gamma cusp. I'll show you the numerics in a second, but it's within an order 1 of the same one. And you can also determine what the analytic structure is in the g plane. There's a branch cut on the g axis. Now there's something really bizarre, which is that the g star, where this happens, is even smaller than 0.25. If you remember, 0.25 was where the radius of convergence was for the exact gamma cusp. You can think of that radius of convergence, if you had a theory that somehow the non-perturbative effects were smaller, then the g star would be bigger. So where the branch cut is, where the radius of convergence is somehow a measure of how much non-perturbative effect is being taken into account qualitatively. And so it's a little bizarre that these trees are taking even more non-perturbative, or more non-perturbative than the exact answer, which was 0.25. I don't know why I wrote 0.24 there. Okay, this is 0.25. So whatever this means, it's not clear what it means, but if you were to interpret it somewhere, it's sort of more non-perturbative than the full result is. And I'll just say it's very simple to determine this radius of convergence. Basically, we take this formula, a over 2 pi g cos pi a over 2. When g is real, we can always solve it for any g. We get an a. But if I make G complex and A imaginary, this equation turns into A over 2 pi G cosh pi A equals 1. And now this doesn't always have a solution. If I plot the function A over cosh pi A, it has a maximum here. And so if G is bigger than this maximum, there's no solution. And therefore, the solution has to have a branch cut at this value, where this has a maximum that you can work out is, you can work out as 0.21, about 0.21. So that's how we figure it out. You get the same answer if you just look at the ratio of the successive terms in the perturbative expansion. Okay, so just to summarize here, I find it rather remarkable that an essentially trivial part of the Amplituhedron combinatorics, together with the also essentially trivial, in this case, way of characterizing the integrals by the boxing trick, already captures all the qualitative features and not too far off quantitatively of the weak to strong coupling behavior here. And, furthermore, we know that the Amplituhedron geometry captures the singularities of planar amplitudes in any theory. It captures all of the singularities that are not at infinity. There's a bunch of singularities at infinite momentum, but all the singularities that are sort of pure infrared stuff are the same for a generic theory. So to the extent that all of this is happening from essentially a kind of the realization that the logarithm is associated with the negative regions for which you can't reach all of these singular configurations, that should be a very general fact. So at least it's some mild hope that these kind of qualitative results might actually be robust and general. I mean, obviously, we're not getting the exact answer. So we're not doing as well as integrability that gives us the exact answer. But we, I think, essentially roll out of bed and get something which has, I think, a lot of the correct qualitative features. And you would hope for something like that if this is a more generic phenomenon. Finally, I want to say something about what is this tree structure buying us? Why did I have to sum over all the trees? Why couldn't I do something simpler? I could just sum all of these ladders. Okay, so now these are not the same as the ladders before, but they're obviously sort of analogous to the ladders. So these are a subset of all the trees where you just sum over these negative geometries. So they're kind of analogous to the ladders. And just like the ladders, they satisfy a linear differential equation rather than this nonlinear one. Okay, so remember, this used to be the exponential of H tree, and essentially by just keeping the first term in this expansion, I'm only allowing the branching from this point to go in one direction. So that's why I just get this big linear chain. Okay, so I get a new differential equation. I can solve this exactly with the same boundary condition, and amusingly, I get for gamma cusp this formula: 4 over pi log cosh root 2 pi g. And you'll notice that this is almost the same as that octagon cusp anomalous dimension that Lance, Benjamin, and Giorgio's defined. And when you look carefully, it's not at exactly the same value of g. So this guy, just summing ladders, is giving us some gamma octagon of g over root 2. So this guy, this approximation, is less non-perturbative. It's root 2 times 1/4, so it's less non-perturbative than the full answer. It also has the wrong analytic property, and it doesn't have the kind of string loop corrections, the 1 over g corrections at strong coupling. Okay, but still at 0th order, it's something that looks like g squared at small g, asymptotes to g at large g, but somehow having the full ladder structure captures more of the non-perturbative physics, maybe overshoots the non-perturbative physics, but it gets the correct analytic structure. The branch cut and the kind of string loop corrections, or the analog of the string loop corrections, are seen by doing that. And this is a table that sort of compares the radii of convergence for various quantities. This is for the cusp anomalous dimension. This is what I just talked about, what we talked about to begin with, the sum over all trees in our model. This is the sum over all ladders, what I just mentioned a second ago. And there's another physical quantity, which is known exactly, a number that are known exactly in the theory, the Bremsselong function, which is the logarithmic derivative with respect to the coupling constant of the expectation value of the circular Wilson loop. And anyway, so the things that we're seeing, this ladder sum that we have, as I mentioned, as a larger G star than that, this tree sum has the smallest of all of them. And anyway, they have similar expansions at weak and strong coupling, except again, of course, the latter sum does not have any 1/g corrections and only has exponentially small corrections. But otherwise, you can see what the sort of numerical differences are, right? You know, so the Kussmann almost dimension at large g goes like 2g, whereas ours goes like 4/πg. Okay, so it's not 2, it's like it's 1.3, but yeah, it's not terribly far off. Okay, so that's really all I wanted to say about this. I think from many points of view, I think maybe the most interesting thing, one of the most interesting things going on here is that there's a direct connection between positive geometries and completely finite amplitude objects. So there's no more excuse not to try to find the direct connection between positive geometries and the polylogarithms. Nothing. There's no veil anymore. Now, we introduced this funny parameter y to deform the amplitude, which is kind of a theory of the loop of loops, where we're imagining that there's a coupling constant that counts the number of loops in these negative geometries. What does it mean? Does it have a physical interpretation? We have no idea. What we've sort of computed is the classical limit, quote unquote, of this quote unquote theory. When y goes to 0, we need y to go to 1 for the real amplitude. And probably most importantly of all, to move beyond the boxing trick, we need to understand these negative geometries more systematically. For example, the first interesting case are these sort of closed chains. But what I kind of hope is that there might be some kind of structure like this, that there's a differential equation or a differential operator or something kind of like that acts on a given geometry and kind of relates it to a sum over other geometries of the same type. And again, the sum over all these graphs, the different graphs would be representing this other direction that we are looking for at the very start. As I said already, this is how it works in our tree examples. Our differential operator hits a tree and it returns another tree. Maybe there's an extension of this where there is some structure that relates the canonical form for any one graph to some kind of sum, whatever this means. This is a very vague statement, but just to give you an idea of the hope, that the biggest hope here is that the other direction we are looking for at the start is here in all the different sort of negative geometries that we could have associated with the amplitude. And I stress again, this organization in terms of negative geometries has no interpretation in terms of Feynman diagrams, certainly that we know of. It's something that's only natural from the perspective of positive geometry, as far as we know. And so anyway, this is, I think, a natural sort of question from the perspective of positive geometry. Let me just mention one thing that we've done. We've done many examples along the lines of what I'm about to show you, but I'm going to show you the simplest one. So we're still not good enough to sort of have under control all of these forms and to be able to do the integrals for these kind of forms. But what we decided to do for a little while is to look at some toy model integrals of this. So this is something that depends on all these loop momentum variables, AB1, AB2, and so on. And it has some interesting dependence on the external points, 1, 2, 2, 3, 3, 4, 4, 1. But we know that the kind of most interesting part of this subject has to do with how the loops talk to each other. So we decided that we would look at a set of integrals. This is now not even obviously associated with positive geometry, but it's a set of integrals where we capture the same interdependency of the loops. Okay, so it's just something like that. But then to make up for the weights, we just put one kinematic point. So one sort of twister at infinity here, except that I squared is not equal to 0. Okay, so one general bitwister I here. So you can think of it as a fat line or a general bitwister. So all the kinematic dependence, there isn't even any kinematic dependence anymore. This is going to be a number because just by weights, this whole integral is just some number times 1 over I squared to the power of L. Okay, but then what you can try to learn to do, at least in these guys, is to see, for instance, clearly you somehow want to break this chain open so that you can do something like boxing on it. So you need to learn how to break the chain open and anyway. So I'm not going to tell you any details, but I just want to give you the flavor of what we found. So in these examples, we find that we can do it. We can cut this chain open, and after we cut the chain open, after we cut it open, now we have something that has endpoints, and that's something that has endpoints we can act on with differential operators. So they satisfy a differential equation. And then after we determine that by the differential equation, we then reintegrate it to go back to the thing that we want. So the result of this process is that we can find in this example that the generating function for the sum of all these chains is an integral. This is what came from sewing them back together of this expression h, where h itself satisfies this interesting differential equation. Okay, so when you expand this out, it's not pure polylogs. It has there are rational prefactors in front and so on. But anyway, in the end of the day, these are just numbers. And from this presentation, you can actually compute what this f of g looks like at small g and extrapolate to see what it looks like at large g. And the amusing thing we found in this example is that while at small g, it's in a series expansion in g squared, at large g, it begins with log g. And then there's corrections that go like 1 over g. So this is subleading to the trees. Remember, we found the trees, like gamma cusp itself, goes like g. But here's another class of graphs. Of course, we don't know exactly how it's related to the one that we want, but it seems kind of to have some qualitative properties in common. At least this set of graphs is not ruining what we found before. It actually gives you something subleading relative to what we found before. So these trees appear to dominate at strong coupling over these loops. Okay, but in any case, these are just some exercises, and we've done a variety of exercises like this. You can glue these things together in various ways, get flower petals and so on. But in every example that we've looked at, it's never true. When you take it to strong coupling, you always get something that does not compete with what we saw with the trees so far. We haven't understood the most complicated graphs, which look like complete graphs now in the negative geometries. Those are the most complicated things that we could look at, and that's still far from our far from our able to control. All right, so that's it for this part, but I can kind of tie the kind of hope of this part to the beginning motivation of the first lecture. So here we see at least a path from positive geometries to non-perturbative amplitudes, from the amplituhedron to anti-de Sitter space. But what I really think is going on here, and I've said for many, many years, is that really from the perspective of the amplituhedron, the most mysterious object out there is the dual amplituhedron. Okay, so there is something out there that makes the canonical form for the amplituhedron obvious, that makes the representation of the canonical form obvious. And if we had it, we would learn how to integrate. And if we had it, we'd perhaps learn what these differential equations are that the integrals satisfy and so on. But the reason I strongly believe that this has to exist is, on the one hand, we have lots of hints that this connection exists purely in the world of positive geometry and canonical forms and all of that stuff. But if you believe that this connection exists at the level of positive geometries and canonical forms, then you know what the amplituhedron is supposed to be about. The amplituhedron, even though it doesn't come from Feynman diagrams and so on, it tells you about its singularities and the factorization and all that tells you about the physics of gluons. So if that's what the amplituhedron is about, physics of gluons, what the heck should the dual amplituhedron be about? And by the law of conservation of things in physics and math, there's nothing it could be about other than strings in AdS. Okay, of course, this is a wild hope, but I think we're beginning to see some evidence for this wild hope in some of these investigations. Because again, I think that the structure that we see with these equations, with these kind of differential equations, are, from this point of view, they're just reflecting. There's just a sort of poor person's way using the boxing trick of seeing how all these regions are connected to each other. And the hope is that the sort of dual amplituhedron is making that presentation manifest, because that's what allows you to sort of see the simplicity of the dependence on the loop momentum. Okay, and with that, that's it. Thank you very much.
Great. Let's thank Nima for these great talks. So I will propose to have 1 or 2 questions now, then have a break before the discussion.
Can I ask?
So questions. Yep.
Hi, Nima. So that was a very nice talk. Yes, it's great to see that you can resum at least part of physical quantities from the Amplituhedron and find some of the structure of the functions that we expect. In quantum field theory and in string theory. So just to again make sure I understand, you say that this y equals 0. There is nothing meaningful on the.
Not that we know. No, I mean, it's something that we're introducing. And by the way, I don't even know if the correct expansion is in terms of the number of loops. I don't know. I mean, it's all we know. All I can tell you that we know. I mean, let's say you've never heard of physics. You're just playing with these positive, negative geometries. It's definitely true that understanding the geometry is much easier when it's trees than the second there is 1 loop. And 1 loop is harder than 2 loops and so on. So there's clearly some sense in which the number of loops in these pictures is grading something, okay? From the perspective of the geometry is grading something. So yes. I think it's natural from the perspective of the positive geometries. I have no idea what it means physically.
For example, yes, in case, I don't know if it's possible to then tune Z, for example. So maybe it could be some limit of the variable that is left. Somehow in like taking y to 0 might correspond to also taking z to some value. I don't know.
Right, maybe. Yeah. Honestly, we have not played. Let me mention another thing that I hope, Georgios, is that someone might just. I mean, this differential equation looks a lot like well, it is Liouville, but along the z equals z bar line. Maybe I can say something else about the answer. I didn't emphasize it, but the answer is a function of log z. That's all, okay? When I sum over trees, it's just a function of log z, whereas we know that the actual function has 2 letters in it, okay? So they're polylogs, but the polylogs have 2 letters. So there's z and there's 1 other variable, which is like z plus 1 over z, if I remember properly. So let's say another variable y, which is z plus 1 over z. So it looks like these trees know only about z, and then maybe it's the case as you add loops that you start getting more y's in the polylogs and more y's in the symbol. But all of that makes one wonder whether there's just some deformation of this differential equation that involves this other y. I mean, it's not an independent variable, but just some deformation of it. I don't know. I'm not remotely an expert in integrable systems, but maybe it would. I don't know. Maybe someone would see an equation like that and it would strike a bell, and they could easily imagine a natural deformation that would have nice properties. I would guess that the likelihood that by slavishly finding these regions and summing them and so on, that we're going to find out what's going on is not that high. As usual, it'd be great if someone just made a guess for maybe some extended differential equation or something. I don't know what. That would just give us a conjectured full, not perturbative answer, and then we could see how it works. At 0th order, it would be interesting if there's some deformation that produced things with y's in it, this z plus 1 over z in the symbol, and produced it in the correct spot. So it has to occur, in the next. It first occurs at the order g to the 4th in this expansion. So already, if someone could find some deformation where the dependence on this other variable came in at sort of 2nd order in the expansion and still gave us polylogs, I think it'll be fascinating. That might already be a start.
Thanks. And let me quickly ask one more question. You said that you need something nonlinear to see more stringy effects. But right. What is it really that, why is it that you need this nonlinearity? I ask because courteously referred to our paper with Benjamin and Lance. But in another paper with Lance and Simon and collaborators, we did resum the double pentaladder integral.
Right.
And that, for example, does have a branch cut. If the question is about the branch cut versus poles,
Right.
on the imaginary axis that is also present in the linear generating function.
I see.
So in this sense, I do not yet, maybe there is something, but I do not yet see what different qualitative features the nonlinear resummation offers.
What about the what kind of corrections are there at? Do you have 1 over G corrections at large G? In that example?
G. No, I think that it's e to the minus G and then more powers thereof. I think this
right.
is
Okay. But so I think maybe the I don't know how important the branch cut is or isn't, but I think the presence of 1 over G corrections is very important. That's really that there are some weakly coupled strings at the other end, right? So yeah.
Okay, no, that probably makes sense. I'll have to think about, but thanks a lot. Yeah. And
no, I mean, but the short answer to the question, of course, I have no idea. I'm just telling you, we resummed what we could resum, because we could resum the whole thing. I mean, all the trees, we did that first, but then yeah, it was interesting to compare it to the latter. Is it's sort of amusing that we got the same gamma octagon. Probably doesn't mean anything, but yeah, but I think that the qualitative feature that bugs me. Well, the qualitative feature that seems more important to me is having the 1 over G corrections at large G.
Great, thanks a lot, Nima.
One more question. Thanks for the great talk. So, if I remember correctly, when you showed the resummation of these connected graphs that are not Feynman graphs, you present as a curious fact that they satisfy the Laplacian. Have this Laplacian action like the boxes do.
Oh, it's not that curious. Yeah, I mean, it's a really simple thing. It's just because the sort of dependence on the last point is fully determined by weights.
Yes.
So it's exactly the same as the boxes. Yeah. So
yeah, but in the boxes, as simple as it is deeply tied to the fact that there's an integrable system for these boxes and the integrability of the quantum field theory there. So, is there a integrable model behind this? Is that a sign for that, you think?
I mean, of course, the integrability of all of n equals 4, you might think is related to all of this, except now we're only looking at a sort of subpart. Yeah, maybe. No, but you know, I'm not the person who knows anything about. I know nothing about integrability, and so I won't even anything I say will be stupid, I'm sure.
It'll be good to see it in a concrete way now. Thanks.